All right, everyone, welcome back to the podcast. I'm Mark.
And I'm Jenny. And Mark, you've been buzzing about this topic off air? Something about a new kind of computer?
Oh man, Jenny, this is pretty cool. We're talking about probabilistic computing. It's a whole fresh way of thinking about how computers function.
Probabilistic computing. So less like the on or off, 0 or 1 bits we know?
Precisely. Think about traditional bits as being absolutely sure it's a 0 or it's a 1, no question. And quantum bits, qubits, can be both at once, right? Superposition. But they need, seriously cold conditions. Miles below 0 sometimes.
Right. Those highly expensive cryocoolers. Like science fiction becoming real, but with a massive energy bill.
Precisely. Now, probabilistic computing uses these things called p-bits. And these p-bits actually represent probabilities. Instead of being definitely 0 or definitely 1, a p-bit can represent, say, a 70% chance of being 1 and a 30% chance of being 0. It's inherently uncertain.
Okay, wait, let me get this straight. So a classical bit is a light switch, fully on or fully off. A qubit is maybe a dimmer switch hovering somewhere in between, but only when it's freezing. And a p-bit is more like a weather forecast. It's giving you the time's likelihood of sun or rain?
Ooh, I like that analogy. Yes, it's kind of like that. And here's the thing about these p-bits. They operate at room temperature. No cryogenics needed.
Okay, that's quite interesting right there. Just the room temperature aspect is a substantial deal compared to quantum. But if they're uncertain, how do they actually times compute times anything useful?
Good question. This is where it gets fascinating. They're not trying to be your laptop or your phone doing spreadsheets or streaming video. Probabilistic computers are designed for specific kinds of problems, especially things involving optimization and dealing with uncertainty naturally.
Optimization problems. Like finding the most efficient route for a delivery truck with 1,000 stops?
Perfect example, yes. Or figuring out an effective way to pack things. Or certain kinds of complex simulations. Problems where there isn't one single, easy-to-find perfect answer, but a landscape of possibilities you need to explore.
So they're not competing with our iPhones, but perhaps with supercomputers or even future quantum computers for certain tasks?
Precisely. The research out of places like UC Santa Barbara and Purdue is pointing to this. They're finding that for these specific types of problems, P-computers can be quite efficient. We're talking potentially significant improvements in energy efficiency compared to even powerful classical chips.
Okay, efficiency is a significant point right now. What kind of improvements are we discussing? Like a little bit better?
Well, here's where it gets interesting. Some of the early, peer-reviewed work talks about 10 to 100 times reduction in energy compared to equivalent computations on high-end GPUs per transistor basis.
10 to 100 times? That's a substantial jump.
It is. And some of the more, let's say, speculative industry discussions and newsletters even mention figures up to 100 million times better energy efficiency in future iterations compared to best-in-class current GPUs. Now, that latter figure seems more about theoretical potential and extrapolation from very small scale, not yet proven experimentally at scale in published papers we've seen.
Okay, so the 10 to 100 times is more grounded in current experiments from research labs, but the potential is significant?
Right. The 10 to 100 range is what we're seeing in actual prototypes described in journals like Nature Electronics. They're building these systems, sometimes even using existing hardware like FPGAs, alongside new kinds of magnetic components, showing real-world gains.
FPGAs? Cool. So they're not waiting for some completely new factory to spin up specialized chips? They can build on existing tech?
Precisely. That makes the path to getting this technology out of the lab and into something more practical a lot shorter. Researchers are using FPGAs to show these probabilistic computers can sample solutions quite fast than just running the same problem on software on a traditional processor. Like an order of magnitude faster sampling rates.
Faster sampling, meaning they can explore more possibilities quicker to find a good solution?
Precisely. And faster sampling with significantly less energy means you can tackle bigger, more complex optimization problems that are just too power-hungry or too slow on current systems. Think about that delivery truck with even more stops, or optimizing supply chains on a massive scale.
So what kind of problems have these prototypes actually solved to prove they work?
They've tackled some classic hard problems. One notable case is factorization, solving problems relevant to potentially breaking certain types of cryptography. Research out of Purdue and also Tohoku University showed probabilistic annealing using hybrid chips could factor numbers faster than classical methods in their experiments back in 2019. It's not breaking modern encryption yet, but it shows the time's potential for this type of hardware to tackle those kinds of problems.
Factorization. Okay, so tackling tough math problems is one area. You mentioned optimization earlier, finding best routes and things. Any specific examples there?
Yes, the Ising model is a common benchmark in this space. It's a mathematical model used in physics and also relates to certain types of optimization. The FPGA-based designs from UCSB have shown notable speedups, like 15 times faster decision-making on these Ising model problems compared to GPU baselines.
15 times faster? And using current tech like FPGAs? That feels quite tangible. It's not just theoretical anymore.
Man, that's why I'm so excited. This isn't just maybe someday. This is happening now, in labs with measurable results. And the potential implications are broad. Think about AI that needs to make decisions based on incomplete data or handle noisy inputs. Tasks that are naturally probabilistic. P computers could be quite well suited for that kind of workload.
Okay, so we're talking about dedicated hardware that's more energy efficient and potentially faster for certain types of problems than what we have now. But you mentioned counterarguments in your research, right? What are some of the potential downsides or challenges?
Good point. It's not all smooth sailing yet. One of the big challenges is complexity and scalability. Most of the experimental work is on smaller scales. Scaling this up to handle problems as large as what supercomputers tackle is a significant technological challenge.
So, building a massive P computer might be harder than it looks?
Yes, it's a significant hurdle. While they can use existing components like FPGAs, building very large probabilistic systems requires a lot of engineering effort to maintain that efficiency and handle the sheer amount of P bits needed.
And does that efficiency sometimes come at the cost of performance for other tasks?
That's another valid point. While they are designed for efficiency in specific areas, they're not intended to replace your desktop doing general tasks. For things that need high precision and speed in a traditional sense, classical computers are still likely to be superior for the foreseeable future.
So, not replacing our laptops then?
Definitely not in the near term. Their applicability is somewhat limited compared to the broad range of tasks a traditional computer can do. They excel where uncertainty is inherent, like in optimization or simulations based on probabilities.
Okay, that makes sense. And the practical implementation side? Getting this out of the lab and into actual products?
That's the final big challenge. Moving from prototypes to commercially viable systems requires developing compatible software, ensuring seamless integration with existing tech, and building out the infrastructure. The use of FPGAs helps, providing a bridge, but widespread adoption requires more.
So while the research is promising and the potential is quite high, there's still a path to travel before we see these in wide use?
Precisely. It's exciting progress, but there are practical challenges to overcome. It reminds me a bit of the early days of quantum computing. Lots of promise, specific use cases showing results, but scaling and real-world application are the next big steps.
That's a helpful comparison. So if listeners are interested in this, where do you think they might see probabilistic computing pop up first? Which industries?
Based on the research and the types of problems they're good at, logistics is a key one. Optimizing routes, supply chains. Finance could see applications in risk analysis and portfolio optimization, where dealing with uncertainty is crucial. Pharmaceutical research, too, for complex simulations.
So anywhere that needs to find good solutions to complex problems with lots of variables and uncertainty?
Pretty much. It's about finding high-quality solutions efficiently, rather than necessarily finding the single absolutely best answer, which can sometimes be computationally impossible for these types of problems anyway.
Okay, fascinating stuff, Mark. It's really something to think about. Computing that embraces uncertainty rather than avoids it. It's quite a different way of looking at things.